We had a lot of contributions to this work from the other two people at Argonne, Nityanan Sidna, who's a postdoc, and especially Marta Shitak, who's presented once already and will present another topic this afternoon. I'm going to try and cover two topics pretty quickly. It looks like I have maybe plenty of time to do it. They both have to do with erosion. One is we've been working over the last 2 years to add sediment transport to our Scour model. And then we've also done analysis of stream stability on a stream in western Iowa and developed a kind of technique for analyzing these things that allows you to do what-if scenarios, but we're using 3D CFD to get the shear stresses on the banks that allow you to do perhaps a little bit better job than you can do with other techniques. So I'm going to talk about the stream in western Iowa first. It's a series of horseshoe bends that's very active. And this lower right here, you can see streamlines going through the bend and how they're all twisted. That shows the secondary flows there. So what we're after there is the shear stresses on those banks so that we can get a rate function for the removal of material. So this just shows a series of photographs, the historic motion of this stream in western Iowa. It's approaching a road there, and the analysis can help you decide, when you need to do something. Close up in the lower left here shows just an arbitrary bank numbering of 1, 4, 2, and 3. So what did we need to do what we're doing? We needed a hydrograph or some stream flow duration curves that we just talked about. We need the bathymetry and the topology of the surrounding farmland there so that we can mesh out in 3D a section of the reach. And we did, and we have it beyond, a little beyond what's shown here. So we run a full 3D CFD through that section of reach, and then we get the shear stresses everywhere. But for this method, we're averaging the shear stresses on the outer banks, where the motion is happening. And we've got a rate of erosion function, which is in meters per second or feet per second. And it's form similar to what Cornell was showing, but you could use anything if if you've got a good formula. What we did here was we had to determine the 3 parameters there: the critical shear stress, the exponent, and the constant out front. We could do that from tests that Cornell or others might run on the erodibility of the banks, or in our case, we had some information about what the soil was like there, and we chose a critical shear stress value, and then we backed the other 2 values out of the historical movement of that stream. Cornell also, mentioned the idea that you could do that. So we had pretty good photographic data going back to 1990, and we split it up, the erosion, into several time periods. And we chose the 2006 to 16 to determine the constants by correlation. And then we also tried to, there were 4 of those banks that we were looking at, and we tried to pick the constants. We kind of did this by hand. You could do a multivariate regression to get those values, but we just did it in a spreadsheet, iterating until we reduce the difference between the actual migration in the photographs and what we were computing. So the way we did this was we run a whole bunch of CFD runs for different discharges. Then we've got a table of discharge and shear stresses, in particular the shear stresses on those banks that we're watching. And we then can get the flow duration from a hydrograph, and we have to interpolate, in a table of our shear stresses to get the shear stress for, in our case, was a particular day. So we were doing this day by day, and we get, a half inch or something of bank migration in a particular day, and then if you have higher flows, might be more, and then you just sum those up over time. So the left side here shows a plot of the migration of bank number 1. It's the one that's closest to the road there. And that's starting in 2005. And then what we fit was the final point on the right side of the lower left. And then you can see that if you add up day by day the migration, you'd expect it to be pretty close, but it is. And then we tried it for the 1990-2016, and we're not as close. There's a point in time around 2000 where we weren't keeping up with the actual erosion. That might have been because we chose the critical shear too high. So once you've got all of this set up, then you can run scenarios, and you can run those scenarios just on a laptop in a spreadsheet to see how far the banks of interest are migrating, to see how sensitive you are and what could happen in the future. So I've got 4 examples of that. The first one is assuming that your hydrograph from the last 10 years is just going to repeat itself in the next 10 years. And what happens, if that occurs? Then this bank number 1, which is closest to that road, moves about 120 feet, and it's getting pretty close. A second scenario is to add an additional 7.5 cubic feet per day to the hydrograph, and then look and see what happens to the migration. And in that case, bank number 1 is migrated over the next 10 years around 150 feet. So of course it's more. And then a third scenario we tried was to suppose that we have more extreme events, but that they happen on both ends. So that we have the same total flow through that section over 10 years, but we have a number of days where there's much higher flow, and that's got to be balanced out by a bunch of days with much lower flow. So the mean is the same, but the standard deviation is larger. And if you then run that what-if scenario, you get about the same migration in that bend number 1. It's around 120 feet over a 10-year period. Then the last example is adding 2 additional one-day 10K events of flow through that reach. And then you have a couple days, to build up to that, and a couple days to drop back down in the hydrograph. And if you do that, then you again jump up to 150 feet of migration in that bend number 1. So there's still a lot of work to do on this type of thing, but it's a methodology where you can use the 3D CFD to get the shear stresses on the banks, and then you can set that up in a way where you can run these what-if scenarios to see what would happen in the future if you are varying the flow rates through there. How am I doing on time? The second topic is adding sediment transport to our CFD Scour model. And at the last conference, we had reached a point where, well, previous conference to that, we had reached a point where we were having trouble. We were using mesh morphing, some advanced mesh morphing techniques that are available in the 3D CFD software. And you've got millions of cells in your domain. And the mesh morphing varies the mesh with the shear stress in a user-defined function that is the rate of entrainment. Unfortunately, these automatic meshing software sometimes runs into problems when you're going into corners and other things, and the areas where the action happens to be often where you have corners and stuff. And that would just cause the run to fail at that point. And then you'd have to stop it, you'd have to go in and fix your mesh and then restart it. So it's taking us 2 or 3 weeks to do something where if it kept going, you could finish in a couple of days. We had resolved that problem because we decided, let's just write our own chunk of software to deform the bed based on the erosion rates. That was pretty successful, and it freed us up to concentrate on sediment transport for over the last couple of years. So we implemented a Eulerian hydrodynamic model for sediment transport. That's where you kind of treat the particles in aggregate, and you have basically 4 partial differential equations to solve if you have a single size. There's 3 components of velocity and then the mass conservation. The other alternative was to track individual particles. That's called a Lagrangian method, and you're solving ordinary differential equations to do that. The limits of our hardware right now on these clusters, kind of medium-sized workhorse clusters, is about 200,000 particles. So going the Eulerian route, where we're tracking, in this phase, where we're tracking the volume fraction of particles as a continuous variable seems much more efficient. And there's nothing really stopping us from using a size spectrum of particles. So you just discretize the spectrum. You can use like 10 size groups. I've done that for various spray type calculations and works well. And you'd end up with 40 equations to solve in the solver. And that doesn't put a big strain on the, it extends your time, of course, but not that much, so it's good. We had to add a friction resistance term because the bed load, the motion on the bed, I've got sand particles bouncing along the bed, and the bed is, providing a force that retards their motion. So that was a tunable parameter, and we tried to tune it as best we could. You'll see some results of that. Then the sediment entrainment rate is based on the type of function that Cornell showed. It's a Van Ryn function, but we could use, any function you happen to come up with. It's very easy to put these in. So it could be a cohesive soil erosion rate function. That's not a problem. Then the deposition rates are calculated based on a local sediment accumulation rates that are calculated and are a product of the CFD computation. We have 2 basic computations we go through. We compute the fluid flow, and we compute the entrainment rate, and then we inject the sediment as source terms in the differential equations, and then you compute that motion downstream and where it settles out. And that kind of reaches, for a particular bed topology, something's close to steady state. Because not much would happen in a 20-minute period. So, it wouldn't change a lot in a 20-minute period. So that's one of our cycles. When we get things kind of stabilized and the convergence of that is the mass balance in the sediment. So when we start going, the sediment gets entrained. It'll be convected downstream, and it'll settle out. Some of it will go out the exit. So we monitor that, and when our entrainment rate and the balances the mass that's settling and going out, then we decide that that cycle is good and done, and we go to this external program to deform the bed. Yeah, basically got that shown in a kind of very simple flow chart here. The blue side is the CFD side. So the CFD computation computes bed shear, turbulent energy, sediment transport, until it's kind of stable in terms of the mass of sediment. And when that's balanced, then we go over to this external program. We displace the bed downward based on the erosion rates. Then we displace the bed upward based on the deposition rates. Then we perform a sand slide algorithm based on the angle of repose. Then we've got a deformed bed. We export that. Then we go back over to the CFD side. We re-volume mesh a slightly changed bed. And we start that up from the previous solution. And then what's going to happen is, as the scour holes form, the entrainment rate is dropping. It's this decay function that Cornell has talked about. So you've got a lower entrainment rate in most cases. Sometimes things change, so some spot may have more. And you kind of have to wait until that change propagates downstream. Then that's a converged CFD state, and you go back over to the other side at that point. So basically, these two plots are showing you each side in terms of convergence. The CFD side is going through many cycles. We cut the entire computation up into about 200 steps or so. So you get the expected scour depth. You could do that by using HEC 18, and then you just divide that depth by 200 to get a target displacement for one cycle. And then that's a parameter in the program that deforms the bed. So it will calculate its own time step for each of these cycles. And it's trying to displace the bed a maximum amount. Well, the maximum amount of displacement would be that target displacement. Then everything else would be displaced less based on the shear stress distribution. So what you see in the blue is the spikes are when we start a cycle up and we've slightly changed the bed. Then the mass is not balanced yet, and we go through that computation until it is. And you can see the blue spike dropping back down to near zero. That's where the mass is balanced. At that point, we go back over to the external program to deform the bed again. So we have a lot of these cycles. On the Scour timescale, the red plot shows the minimum elevation of the bed. And you can see when you start out, so we just arbitrarily, when we're starting, these are flume tests that we're running, so we just arbitrarily set that at 0, and you can see the elevation dropping as scour holes form. And it's kind of a decay function, and if you heard Cornell's talk yesterday, it's that type of function. And it, first it goes very quickly as the scour holes form, it slows down, and eventually it goes asymptotic where things aren't changing anymore. At that point, we decide we're done, that the computation is done. So you can see that happening, and you can kind of see the amount of time it takes. 86,000 seconds is a day. So this was a cylindrical test. We've also reached a point, so we got all the mechanism for this to happen pretty much working, and now we can concentrate a little more on the actual physics. And it turns out to get a good bowl-shaped scour hole around a cylindrical pier that you need some correction factors to the critical shear stress. So we had a factor in there previously for the bed slope. So if you're trying to push particles uphill, then the critical shear stress is higher. If you're downhill, then the critical shear stress is lower. So that depends on the flow or the shear stress, the direction of the shear stress at a point in the flow. Because you could also be trying to push particles, in a constant elevation direction. Then that K factor for that would be 1. So the two other ones that we added, and they're to account for typically downflows at the leading edge of obstructions. They're from Wyming Wu's work. So one is related to the vertical pressure gradient, and the other one is related to when you have a downflow, the angle of the downflow with respect to the bed in the near vicinity of the bed. So I've got here the cylindrical pier test, and it's one that was run at Turner Fairbank. And we found that we're also having to try to match the lab conditions pretty closely. So when they're running their tests, they're trying to achieve a uniform velocity distribution all the way across the inlet, but it's not. Fortunately, they had some measurements for us, and you can see that in the upper left there. So there's some slight variation in velocity profiles across the width. We try to match that so we come pretty close to what they have in terms of results. And we are getting pretty close. This slide shows kind of the evolution of our scour holes over the past couple of years. At the last conference, I showed the one in the upper left. We didn't have any sediment transport, so there's a trench behind the pier. What you're seeing is color plot of elevation, so the red is high and the blue is low. Where we were kind of at the beginning of the summer was in the upper right here, and you could see the scour hole has kind of a butterfly wing form to it. It's not the nice bowl shape. And adding those two extra factors into the critical shear stress produced this nice bowl-shaped hole that's in the lower left here. And then the experimental one from Turner Fairbank is in the lower right. So we're getting pretty close. That friction factor that I was talking about, the bed friction factor between the bed and the particles in the bed load, that's a tunable parameter. So you can see that the high spot in the mound downstream of the pier is right on, looks like a little bit too far down, too many diameters down compared to the experiment, but that could be adjusted with some more fine tuning. Of course, you have to tune that for that one, and you also have other geometries. So we're getting close, but yeah. And this is rectangular pier, so that's a pretty different geometry and a good thing to test that. So we did that, and you can see kind of the mound off the trailing edge of the rectangular pier forming, and then you can see the mounds on the leading edge of the rectangular pier forming, and they're forming in approximately the same positions as we had from the lab. And that's also very encouraging. And we put in the variations and the velocity profiles across the inlet that we got from the Turner Fairbank data. And this is the last one I have. You can do interaction, between different obstructions in the flow, and you can find out how they influence each other. So we found a paper that did a whole bunch of tests with two piers, one behind the other, with different distances. This is just showing a 5D separation. It's close enough so that the sediment picked up out of the first one is dumped into the second one. So up in the upper right here, you can see the experimental result. The upstream pier had a scour hole that was 6.8 centimeters, and we got 6.2 without tweaking anything. And then the downstream pier, because it's filling in after you get far enough along, its depth was 3.5 centimeters, and we got 3.1. So we're pretty happy with that. It was the last thing we did. And that's basically what I have. So we have a method here that's now starting to look pretty good, like it could really be useful. Thank you. Any questions? Yeah, so with the size compute cluster that we're using, plus you run into problems. We chose not to do the particle tracking, because if you track particles, the limit on our compute equipment is about 200,000 to complete the computation in a reasonable time. And you need, well, that might be a statistically significant sample. It might be good enough, but it's a lot easier to use what they call an Eulerian method. So we're tracking the particle phase volume fraction. So it's a multi-phase flow, and we have exchange terms between the fluid and what's called the condensed phase, the particles, so that there's drag exchange terms, and gravity is acting on the particles, and there's also this bed friction that's acting on the particles. So in one computational cell, the same thing happens to all the particles. So in a Lagrangian approach, you could have particles cross each other in the cell. In the Eulerian approach, you don't, but it doesn't really hurt doesn't hurt the model that much. And it's very easy. It's very fast to solve those equations. And as I said, we could go to a size spectrum to have different sediment sizes pretty easily without making the computation too long.